Well, good morning to all. Here we are on actually day 2 of this home online instruction. And day 1 was actually didn't go as well as I'd hoped. I did a wonderful 50-minute silent movie where the audio, of course, did not function. But not know that until the very end. At any rate, we're going to start over. And let me erase this. And that was sort of an introduction. And then yesterday I did send you a photo image of what I was beginning to cover, and so I wanted to kind of go over that just briefly with you here. And it's kind of small, but I can go over it at any rate real quick. But before I do that, let me talk to you just a review to kind of what I sent the email out also yesterday about what's going on here going forward. And again, I will be giving 3 50-minute lectures per week covering the material that we're going to try to cover from here until the end of the semester, which is May 12th. And then, we were going to have a regular, we have scheduled 2 more exams, and we'll have those exams at some point. I'm not quite sure how all that's going to work, but I'm working on that and get that resolved this week. And then we'll have our regularly scheduled final exam as scheduled in the from the registrar's office. So that's nothing has changed there with respect to the dates and times for the rest of this semester. So that's where it's going to be, and we will do our best to cover the material as best we can, given the conditions that we're currently working under. Let me see if I can adjust the frame on this so to blow that up so we can look at it a little bit closer, and then we'll get started on the new material. Okay, now, before we left campus, we introduced phase diagrams, and obviously they're used to predict and rationalize various microstructures of various metal alloys, and primarily based upon just temperature and composition. And it helps us to understand both phase formation and transformation that are caused by the variances of the temperature and the composition in each one of these alloys. So we're going to look at 2 basic types. We're going to focus on two basic types of phase diagrams, and they're all predicated on solubility. The first one, which we're going to basically generally call type 1, has complete solubility. In other words, in solid and liquid states, it mixes in all proportions as a liquid and solid. In this type 1, there will also be a change of state, which means we'll go from a liquid to a solid and back to a solid to a liquid. And then also, most importantly here, to tie into the solubility is the fact that these 2 elements that are being joined together as an alloy have to abide by the Hume-Rothery rules, which you recall what those rules are from your old days of substitutional area on atoms. So, and then we've given this particular type 1 a formal name, calling it a binary isomorphous. And again, we're doing just binary diagrams, meaning just combining 2 elements at once. And the isomorphous just means for basically the same structure. And you will always know what an indication of a binary isomorphous diagram looks like by its shape. And we've given it what we call a lenticular type of a shape on the diagram. which is displayed currently right here as we put in class. Then we'll go over this just a minute. But the second type, which we probably will not get to today, but I'll start with that probably tomorrow, is what we're calling initially, generically speaking, type 2. That does not have complete solubility, has only partial solubility with the two elements. There will be another change of state, but this particular diagram is unique in the fact that it does have what we call a eutectic point, and that eutectic point just shows the lowest melting point on that phase diagram for both elements when they're combined, and that's kind of a unique situation, and we'll show that to you in detail starting tomorrow. But of course, we call that diagram a binary eutectic diagram, and again, it's just two components being alloyed together, and initially we're just calling these two elements A and B up here in this example. So here is a traditional standard type binary isomorphous phase diagram. Here's this this lenticular shape area here, which forms the two-phase region, because on top you have a single-phase liquid, on the bottom you have a single-phase solid, and then of course we just have the temperatures. On the left would be the temperature for A, and then indicating the melting temperature of A right here, and the melting temperature of B on the far other side, on the right side, up here at a higher temperature. And so here is on the bottom, of course, the composition percentages. And so at this point, it's 100% A. On this end, it's 100% B. And so, as I told you before, we're always moving back and forth from left to right in terms of the composition of B. So this might be, for instance, this might be 75% B, and this might be 25% B down here. So we're always moving from left to right in terms of this far right-hand element, whatever that might be. So 2 points of interest here, or actually 2 lines of interest here. The first line of interest would be the separation between the single-phase liquid and the two-phase slush area in here of liquid and solid, and that line is called the liquidus line. The liquidus line. And it represents the lowest temperature for only liquid to exist at any composition. Okay, the lowest temperature where only liquid still exists. From there it transforms, okay, and that's this transformation right here, transforms from a liquid to a two-phase region of liquid and solid, as denoted right here. All right. And then below that is the solidus line, but this is the highest temperature at which a solid remains intact exclusively. And it, again, shows the highest temperature where it's only a solid before it transforms into this two-phase region of a solid and a liquid, as represented here. Okay, so this two-phase region traditionally it's called kind of a slush because it contains both liquid and solid, all within the boundaries of this lenticular shape right here. Okay, so what we're going to do now is draw another binary isomorph diagram and begin to analyze some things here for you. So let me draw the diagram and we'll begin the analysis procedure after another swig of coffee. Normal routine. Okay, so let's go moving forward here. Let's do this with this one. Okay, so we're going to draw another diagram, and it looks something like this. All right, and again, we're going to have composition down here. We're going to have a element here of A, element here of B, and then we're going to have various temperatures up here, and then various compositions. Okay, and of course this is not going to be to scale, NTS. And so now let's just arbitrarily pick a couple of areas here. Here's a point, and here's a point here, and those represent the melting temperatures. All right, so this is going to be melting temperature for A, and this is going to be the melting temperature for B. Okay, so let's draw the attempted lenticular shape drawing right there. And of course up here we have all liquid, down here we have all solid, and this is circle P equals 1, this is circle P equals 1, and of course in here we can have just liquid and solid, and we'll have circle P equals 2 inside this two-phase region there. Okay, now let's look at what's going to take place here on this diagram. If we know if a temperature and composition, and let me see if that now see, I got to readjust the camera here. All right, that's better. Okay, sorry about that. So if a temperature and composition are known, we can determine several things, and what we're doing here is basically let me get another point here, and we'll just put up some compositions here, and let's just draw a line here, and let's call this 40%. But you know what? Let's change this from just A and B. Let's put real elements in here, and let's change this to copper. Let's change this to nickel. Okay, this is a classic example of a binary isomorphous diagram of copper and nickel, because they do mix in all proportions, liquid and solid state. So we're going to look at three specific areas here, here, and here, and let's go over here, and let's call this arbitrarily 1300 degrees. Let's call this arbitrarily 1250 degrees, and down here we're going to call it 1200 degrees. Okay, so now you see we have a temperature and a composition known in this case we have three locations. Okay, we have three locations. All right. So if we know that where we are on this with respect to the temperature and composition, we're going to be able to first determine what phases are present. Okay, what phases are present. All right. All right, and the second thing we're going to be able to determine is determine the composition of each phase. All right, and then the last one we'll be able to determine the relative amounts, which is basically same thing as the weight percent. All right, and that's just how much liquid is present or how much solid is present. So those are the three areas that we will be analyzing in each one of these locations on this particular diagram for copper and nickel. What phases are present, determine the composition, of each phase and determine the relative amounts of each phase. All right, of each phase. Okay, now let's look at, and what we're going to do is we're going to have what I call 3 crucibles. You know, something you can put, you know, liquid metals into, okay? And they're going to be, one is going to be at 1300 degrees, the other one's going to be at 1250 degrees, and the other one will be at 1200 degrees. Okay, so let's see if we can go through these lists here and see what's taking place. Okay, at the 1300 degrees, which is up here, we're going to have what phase are present. It's going to be all liquid. Okay, so you know, I know that's not what it looks like, but basically it's going to be all liquid. Okay, and from that, we're going to be able to look at this and what determine the composition of each phase. Well, the composition clearly states that this is 40%. So at that point, the liquid is 40% nickel. And determine the relative amounts of each phase, well, it'd be 100% liquid for there. Okay. All right. So let's move over here to let's jump and skip to this one, the solid phase. And you know, if we have a solid phase, it's going to be completely solid. So it's just going to be made up of, you know, multi-crystal, multi-grain solid. And we always call these solid grains of a metal in terms of a lowercase Greek alphabet, alpha, beta, gamma. So let's just call these alpha grains. We got big alpha grains sitting here. All right. So what phases are present, of course, would be all solid. Solid alpha grains are present. All right. And then determine the composition of each phase. Well, again, it doesn't change. It's 40%, so it'd be 40% nickel. So the liquid and the solid phase are both at 40% nickel, which you would think would be the case. All right. So now, determine the relative amounts of each phase. So now we want to, in this two-phase region, now we're in a two-phase region, of course, and now we need to determine, because we're having a liquid and a solid, and so when we do this, we're going to have, here's the solid portion, of course, with our alpha grains, and then up here is going to be our liquid. So the question is, what is the composition of the liquid? Composition of the liquid. And what's the composition of the, of the solid. Let's just put this liquid. And composition of the solid. All right, so at this point, we don't know what that is. All right, so here's where we need to, and I'm going to come over here and draw a larger one right quick, kind of a view. This is a sort of a blow up of that diagram right here to here, because we need to construct something, a very important piece to this. And what we're going to do is we're going to draw an isothermal line. We know this is at 1250. See this line here, 1250. So what we're going to do is we're going to extend this line and intersect, first of all, the liquidus line, and then we're going to keep drawing it horizontally until it intersects the solidus line. All right, and that's going to define what we call two end members. So I'm going to come over here and do that. And again, it's just a solid, straight, horizontal line. But it creates what we call two end members. And this line is referred to as the tie line. It's called the tie line. It's an isothermal line. All right, it's an isothermal constant temperature line, but it's called referred to as the tie line. All right, now it defines two end members. All right, and we're going to have one on the liquidus side, and we're going to have another end member on the solid side. Okay, now what these end members represent, the end members represent these solubility limits of that mix. Okay, so this is what we're going, and this is going to be an actual percentage. All right, and let's just, so we're going to set this thing up for something else later. Let's just call this point a composition star C for liquid, and this will be a star C for solid. Okay, C meaning just the composition, and let's just call this 40% just the standard C. We'll do that for later. Okay, so, and we have here drawn down here, this is the standard C, which we know to be 40% nickel. Okay, so that's this point right here. All right, so what we need to do in order to find these two compositions, what we need to do is to take this, where this tie line intersects the liquidus line, we'll just drop it straight down and just arbitrarily pick out a percentage, and we're just going to call this, if we go down here again all the way to the bottom, which is called that 32%. Let's call this 32% right here, where this intersects. Now where the tie line intersects the solidus line, come down here, and we're just going to arbitrarily call that 45%. 45%. And so this would be dropped all the way down, and this is going to be messy, but anyway, this is going to be at 45%. All right, so essentially, let's get rid of this. All right, so we have, let me get rid of this so we can kind of show it better. So this is the original C. This is C star L. This is going to be C star S at 45%, and this is just the original C at 40%. Okay, so we've got a 32, a 40, and a 45%. Okay. Values. All right. So we've just answered that question. For the liquid, the composition will be 32% nickel. For the solid, the alpha solid, is going to be 45%. 45% nickel. All right. Okay. So that takes care of this one. It takes care of this one. And now we're on to this last one. Determine the relative amounts of those. And let's see. We're going to do something we call the Leverett rule in order to do this. Okay. So in order to find this last question is, this is number 3. How much liquid is present and how much solid is present? Okay, that's the last one. Okay, this is number 2. All right. Okay, so to do that, we're going to use something known as the lever rule. Very straightforward. It's almost kind of like taking a simple beam and solving for the support reactions with the concentrated load in the center. Basically, what this amounts to. Very simplistic, but there's one little caveat you have to remember when designating these values. Okay, so let me write this in terms of the variables here. Just the letters. So I'm going to be using the C star L. I'm going to be using the C, and then I'll be using the C star S. All right. Okay, so let's look at how much liquid is present first of all. So we want to do percent liquid, and you would write it just like that, percent liquid, and percent liquid would always be, and let me draw it this way, would always be the opposite leg. Okay, so in other words, you're always going to start at this main composition, this C, and if you're wanting to know what the composition of this is, you have to take the opposite leg of that. So in the numerator, it's just a little division here. So we're going to take this value, subtract it from this value, and come up with, the numerator. Okay, but again, it's always going to be the opposite leg, not to the liquid, even though we're wanting liquidus. And if you go back to, when you're trying to do a support reaction, that's what you do the opposite leg. All right, to find this leg. So it's basically like a moment equation. So at any rate, we're going to take a and remember that there's the negative sign means nothing, it's meaningless. So it can be either way. So we're just looking for the value between these 2 points, between these 2 percentages. So essentially what we're going to have is C minus C star S over the entire length of that tie line, which would be C star L minus C star S, and then since it's a percentage, you'd obviously want to multiply times 100. Okay. So now plugging in real values here, this would be 40 minus 45 divided by 32 minus 45, and again, negative sign means nothing to us. Okay, so when we do that, we're going to essentially come up with 38% liquid. All right, 38% liquid. So this is going to represent 38% liquid. All right, and you probably can't see that. Well, yeah, you barely could see that. Okay, let me write it over here too. 38% liquid. All right. Now, the other thing that this tie line does, along with giving us the solubility limits, it also represents the notion of phase separation. This tie line also denotes phase separation, and also conservation of mass. Conservation, and see, this is getting messy. Conservation of mass. So this tie line again evokes these solubility limits, which basically is showing a phase separation from here to here, but it also evokes this conservation of mass. In other words, in this region right here, along inside this tie line, it's either going to be liquid or solid, and then the two have to equal to 100%. So that's what this means, conservation of mass. So therefore, if you wanted to look at percent solid, you simply could take this 38% and subtract it from 100 and come up with 62. But of course, we don't want to assume anything right now, so let's just do this again one more time for the solid. All right, now we're going to be looking for the percent solid. In this case, we're going to have, again, the same C, but again, it's going to be the opposite leg. So if we're wanting solid, we're going to want this little, wanting this, okay? That would be for the solid. So it would be C minus C star L over the entire length, which would be, again, C star L minus C star S times 100. Okay, and then now plugging numbers, we would have 40 minus 32, okay, 40 minus 32 over 32 minus 45, all right, and believe it or not, when you divide that out and multiply it out, you're going to get 62%. So we've just answered both of these questions. What is the fractional amount, or was also referred to as the relative amounts, in each? So we have 62% solid, all right, and 62% solid, and hold on, this goofy timer, I gotta look at this. All right. Hang on. Okay. We have 62% solid here. So the solid is at 62%, and the liquid is at 32%, as far as how much is actually there. Okay. But what we also know is that this liquid, the 32% liquid, is, how much do we say? 38. Okay. All right. So this is 38%. Sorry about that. This is 38% liquid. But this 30% liquid is actually 32